Hello, Dr. Dolman. Welcome to Teach Me number 4. So in this one, I wanted to talk about the cell cycle, errors, and disorders. So when we were in class and we were discussing mitosis, I thought mitosis was really interesting, but I also wasn't aware it was so heavily regulated. I guess that makes sense, thinking back on it. But I didn't know that there was a checkpoint at G1 going into S and G2 going into mitosis and metaphase to anaphase. So I thought that was really cool, and I wanted to explore some issues that can arise if, for some reason, that becomes not regulated. So that's what I decided to get into. So first, let's just start with how does the cell cycle work? Just review. So recall, the point of the cell cycle is this is the process by which the cell is going to grow. It'll duplicate its DNA and then it'll divide into two new cells. So this is obviously a very heavily regulated process. We want to ensure that this DNA that's being duplicated, for one, is good and not damaged. And then we want to ensure that whenever we decide to duplicate the cell, that it's got all the nutrients it needs, and that it's in a good place to divide. So we have three major phases. G1 is cell growth. Our cell is literally physically growing. It's checking its environment, making sure it's safe to duplicate, making sure we have sufficient nutrients to duplicate, and yeah, it's preparing to duplicate. S phase or synthesis phase, we are literally duplicating the DNA. G2 phase is just another growth phase. However, at this point, we're really trying to prepare for mitosis or for duplication of the actual cell. We're checking that duplicated DNA for any errors and then prepping for mitosis. And then in phase mitosis, we're duplicating into our daughter cells. So we've got three normal checkpoints, and this figure comes straight from the slides. We've got a checkpoint at G1 going into S phase. We have a checkpoint G2 going into in phase, and the checkpoint in phase, or rather metaphase to anaphase. So a couple things that we didn't necessarily discuss in class were some key proteins that are in this step. It's not super important that you memorize them, but just understand that at G1S phase, we have P53 and this RB protein. We'll come back to that. That's going to be a pretty important player. And then for metaphase to anaphase, just take a look at cohesin, MAT2, APCC. Those will come back in a little bit. But yeah, these are very important. Like I said, heavily regulated. We want to ensure that at every point of this cycle, all of our junk, all of our DNA, the chromosomes are all how they need to be. Okay, so cancer is kind of the low-hanging fruit. This can occur in just about any phase. However, according to the research that I was looking at, it seemed like a lot of error occurred from the G1 going to S phase. So let's look back at that P53 and RB protein. In the figure, all it's demonstrating is normal P53 and RB working. I can't explain this too in depth. This isn't something we really talked about, but just understand that these proteins are regulatory proteins that will hinder us from entering into S phase for whatever reason. So in cancer, something will affect P53 and or RB. This allows damaged DNA to get replicated over and over again. Mutations can accumulate every cycle, and the cells divide when in reality they shouldn't be dividing. So we have P53 mutated in many cancers, and we'll come to that in a second. Retinoblastoma is an inherited RB mutation. And then in HPV, human papillovirus, we have two proteins, E6 and E7, that will destroy and inactivate P53 and RB respectively. So let's take a look at some of these. So this is looking at that HPV, how it had that E6 and that E7 protein. Well, if you see, it seems that they bind or something to both P53 and RB respectively. Well, with P53, we experience total degradation. The P53 breaks apart. So if our inhibiting protein, our P53, is broken, this just allows us to go from G1 to S, regardless of if we're ready or not, regardless of if anything is damaged or anything's not how it needs to be. Um, And then it appears that the E7 just stays binded to the RB, which will have a largely similar effect. This is again just another picture of the HPV. I just like this one. You can see the E6 binding to the P53, and then the P53 ends up degrading and breaking apart. So yeah, just something to keep in mind. Whenever P53 or RB are compromised for whatever reason, we experience the loss of that first checkpoint, which allows us to duplicate DNA that probably isn't ready. Okay, disorder number 2, aneuploidy. So aneuploidy is when cells divide and end up with the wrong number of chromosomes. Um, so if we think back to metaphase going into anaphase, we have our chromosomes stacked up with each other, right? Or our sister chromatids. And those kinetochores are going to come and they're going to touch. And every sister chromatid has one and another one. So every chromosome has 2 kinetochores, and then every sister chromatid has 1. And what the cell is doing is it's sensing tug. And if there's equal distribution between both sides, equal tension, we're good. So in this step, something happens to some of the proteins in that phase where there is not equal tension. It could be a variety of reasons why they don't split evenly. And when that happens, we end up with daughter cells that have uneven amounts or wrong number of chromosomes. So in this picture, we've got 3 chromosomes in for chromosome 21. This is Down syndrome. We'll come back to that in a second. So there's a couple disorders that are associated with aneuploidy. Number 1, and kind of the most common one, is Down syndrome, where we have 3 copies of chromosome 21. Number 2 is Turner syndrome. I was vaguely aware of this one, but I didn't know what it was super in depth, where we have the loss of 1 X chromosome. And then number 3 is Klinefelter syndrome. We have an extra X chromosome in males. So let's kind of look at these real quick. So in Down syndrome, we get that extra chromosome for chromosome 21. And I like this picture because it showed a lot of the additional complications that can arise from just this 1 extra chromosome. Usually when discussing Down syndrome, I feel like it is very explained that it's a mental thing, right? There's a lot of uh, what's the word I'm thinking of? Intellectual disability that comes with Down syndrome. And we know the obvious physical characteristics, but there's a lot more going on here that I was not aware of. Big toes that are widely spaced, an enlarged colon. They are at greater risk for congenital heart disease, intestinal blockages, hernias, abnormal pelvis. Like lots of these things I had no idea were associated with Down syndrome. I was only aware of, I guess, the super obvious ones. So this is a really cool figure to see. Turner syndrome. So with Turner syndrome, the biggest thing I was able to find was that it doesn't have a whole lot of intellectual complications. It's primarily a physical thing. These individuals are of shorter stature. Their necks are webbed, so it looks like they've got a smaller neck. And then they've got some of these other things. We have some issues with the aorta. We have a different kind of shaped face. The hairline goes down really low, broad chest, widely spaced nipples. I mean, a couple things. So it's just very interesting to see what can happen with the lack of just 1 chromosome, or rather, the loss of the next chromosome. Finally, we have Klinefelter syndrome. So remember, men are XY. We have an X chromosome and a Y chromosome. With individuals with Klinefelter syndrome, we have 2 X chromosomes and a Y. Well, when we look at the characteristics of Klinefelter syndrome, we see that it will give men female characteristics, which makes sense. If women are XX and men are XY, we've got a man that's XXY. It makes sense that they've got some of these more feminine traits. So if you look at what the figure says, we have slightly feminized physique, poor beard growth, We've got some amount of breast development, perhaps, osteoporosis, smaller testes, things like that. And if you look at causes in this other one, it's just a random error during meiosis. It's a little different, but um, an extra copy of that X chromosome. Um, so yeah, I mean, very interesting. I had never heard of Klinefelter syndrome prior to this, so it was very cool to see. Um, so references, um, yeah, I didn't actually explicitly point these out where they were, but G1S phase appears to, or rather, cancer appears to occur during G1S phase. That was from my first citation, and then I was looking at kind of how this HPV, how this had some association with cancer via this reference. But yeah, I really enjoyed this topic. That was very interesting. Um, yeah, I really think cell biology is really, really cool. Thank you for listening, and that's all that I got. Goodbye.